Great. Well, yes, thanks very much for the opportunity to come speak. It's a real pleasure to be here. So my first lecture today is I want to broadly speaking, I'll be talking about the minimal model program for foliations in these talks. But today I wanted to start by talking about the birational geometry of surface foliations. And so this is a story that goes back a few years. And so I'll be liberally making use of ideas due to three people, so Brunella, McQuillan, and of course, Mendes. So like I said, I'll be liberally using their ideas to explain a sort of program of classification. So the goal, I guess, the main goal of these talks is the following. So this is our dream, is to classify foliations on projective varieties. And I should say, I'm thinking always over C, so holomorphic foliations on projective varieties. Okay, as stated, this is kind of a ludicrously broad goal. So maybe to be a bit more specific, a bit more concretely, we should group foliations into natural families based on sum invariance. On some invariants, and these invariants are to be determined, but discovering what these invariants are will be part of the goal of this lecture today. So, so like I said, this is our dream, and I'm going to try to explain how this dream becomes something of a reality in the case of surface foliations. Then in the subsequent talks, I'll explain progress on this problem in higher dimensions. Okay, so let's first do a first attempt at this classification. So X is, let's say X is a surface. F is a foliation. And let's let X inside X be a general point. And what I could ask is I can let L of X, so L of X be the leaf. The leaf through X, and I can consider its universal cover. Well, L of X is the leaf is abstractly just a complex curve. So by the uniformization theorem, the universal cover of L of X is one of three things. We have three possibilities. So one, L tilde of X could be P1. It could be just the whole complex plane. Or the third possibility, L tilde of X could be just the disk inside the complex plane. So this is just the uniformization theorem. So this is our first pass at maybe grouping foliations. We think, well, maybe what we should do is we should try to group foliations into three basic classes based on what the behavior of a general leaf is. This is not such a, this approach has some benefits and some downsides. So I want to make a few remarks about attempt one. So One is just that the classification is birational in nature, by the way I've set it up. So but when I say birational in nature, all this means is we only care what's happening. We only care about the foliation on some open dense subset. I mean, we're free to throw away. I mean, because we're only looking at the behavior of the foliation around the general point. We're sort of free to replace X by some big Zariski open subset of the surface and recompactify that if we choose. I guess going on with this, if XF is a foliated surface, we can always blow up the foliated surface. Blow up at a general point. So call it X and X, and we get a transformed foliation. So we have the blow up of X at a point, but we can also blow up the foliation on F. I guess I just want to pause here. So I know this is supposed to be more of an introductory thing. I just want to just pause to emphasize that we can really take the birational transform of a foliation. So you can think of this either, in this case, F, let's say X is smooth, F can be defined by a single vector field. So all we're doing is we're taking a vector field defining the foliation, taking its transform under the blow up, and that defines a new foliation up on the blown up space. So alternatively, this is the same thing as what you do is you can take the pullback along the blow up morphism of TF restricted to X minus the point. So this is, you can just pull it, so you restrict your foliation to the open subset where your blow up is an isomorphism. And then you intersect it with the tangent space, or the tangent sheaf of X. Yes, exactly. And yeah, you take saturation and everything, and then saturate. And yes, thank you. Okay, so I'll pause here because this is a very important point that you can blow up foliations. So it's a basic fact, but it's integral to everything that's going to go on from here on out. So again, I just wanted to pause here just to check if there's any questions about what the definition is, why it's well defined. Yes, please. My foliations are always saturated. Yeah, so maybe I'll put on this board just to fix some notation. So for me, ultimately we're gonna have to work with normal varieties, but if you want to think smooth, that's totally fine. So F is the data, so a foliation for me is the data of TF inside TX, which is a coherent, saturated subsheaf such that it's closed underneath Lie bracket. If it's not saturated, I'll call it an integrable distribution. But yeah, so this is going notation. So for me, this is what a foliation is. Sorry, thank you. Closed under Lie bracket. So it's integrable. And so yeah, if you pick your other favorite definition of foliation, and it's probably equivalent to this. I guess I also want to emphasize that I'm allowing my foliations to be singular, but I guess this is a conference about singularity, so that's not so surprising. Okay. Okay, great. Any other questions on this? Like I said, this is a small point, but it's the beginning of a much larger story. So, so the other remark I want to make about attempt 1 is that it's a bit too coarse, I think. And I just want to give a concrete example why it's perhaps a bit too coarse. So, this is more of a philosophical point. So let's consider two examples. foliations. So let's consider x1 is just just the foliation given by an isotrivial fibration, so C cross F down to F, where I'm going to assume that the genus of F is at least 2, or sorry, genus of C is at least 2. And then x2, let's say x2 is a non-isotrivial fibration. In genus bigger than or equal to 2 curves. So these really exist. I guess blow up your favorite pencil for an example. So the point is that from the perspective of attempt 1, these foliations belong exactly to the same class. The universal cover of a leaf in both cases, so is just the universal cover of a genus greater than 2 curve, which is just the disk. So in both cases, so these in some sense fall into the same classification in terms of this classification schema of attempt 1, but they're very different foliations. And philosophically, we wouldn't want to group these two foliations into the same family. So this, I guess, is the starting point, is that we should, I guess if you believe me that isotrivial fibrations and non-isotrivial fibrations are very different from each other, which hopefully you do, then you'll agree that attempt 1 is a much too coarse attempt at understanding or classifying foliations on surfaces. So what's the next best thing? So I don't know if this, so I guess Luis should explain what maybe the inspiration that he came to for understanding this classification, but this is my twist on it. There's an invariant which tells these two apart, and it's the canonical class. So what we define is we define K of F to just be minus the first Chern class of T of F. So you should think of this as this is in complete analogy with the canonical class of a complex manifold or complex variety. So this, maybe I want to put a big orange box around this because this is going to be one of the most important things in this whole series of lectures. This is sort of our starring actor. And the thing to observe is that in this case, so this is some cohomology class. So in this case, kf squared is equal to 0. So it's a cohomology class. And so we can intersect it with itself. And in this case, kf squared is 0. But in this case, kf squared is positive. Let's see here. I guess if it's a smooth non-isotrivial fibration in genus 2 curves, kf is ample, right? If it's, yeah, minimal fibration, yeah. So I'm assuming, yeah, so I guess it's a smooth, it's a Kadara fibration, I guess is what I'm saying, a smooth, yeah. Otherwise, yeah, you're right, we'd have to do some bit more work, which we'll get to, but yes, thank you. Okay, so right off the bat, we see that our canonical class is a better invariant in some sense. It's refining attempt 1. Attempt 1 is a very reasonable attempt. And I wanted to bring up attempt 1 to conceptually link what we're doing to the uniformization problem. Because what we're going to try to do is create a generalization of the uniformization theorem for foliations in arbitrary dimension. And we're going to start doing it using this invariant called the canonical class. So let me So let me then explain what attempt 2 is. And attempt 2 is necessarily going to be a bit vague, but hopefully as I go through my lecture today, I'll be able to explain a bit more how attempt 2 really works. So attempt 2 is the following, we should attempt a birational classification guided by KF. Oops. Okay, and what does that mean? So this is what we should do is we should find a birational model where KF becomes simple. And I'll explain exactly what I mean by this now. So what we predict is that, so given xf, we conjecture that there exists a birationally equivalent surface vibration, or surface foliation, so birationally equivalent. So in other words, xf and x prime, f prime, you can do a bunch of blow-ups and you get the same object eventually, such that either one of two things happens. So one, we find some model where x prime down to b is a P1 bundle, and f prime comes from this bundle structure. So i.e. the leaves of this foliation are just the P1s, so leaves are P1s. In the fibers. Or KF prime is NEF. And let me recall what NEF means. So go over here. So recall that a line bundle or a divisor, so X, let's say again, is a variety. L is a line bundle or divisor. We say that L is NEF if L dotted with C is non-negative for all curves C inside X. So it's some cohomological condition. Okay, so why NEF? So there are lots of reasons why we should try to get to a model where things are NEF. I'm going to give you an exercise, or I'll give some people an exercise. I mean, you don't have to do it, but if you're a PhD student, you have to do it, I guess. The exercise is the following. So if xf is a foliation, a foliated surface, and x is not a singular point of the foliation, and we blow up x, Is not, thank you. Perfect. Is not a point in the singular foliation, and we blow up the point. Then kf, or k of the blow up of f, dotted with the exceptional curve, is equal to -1. So this is a good exercise if you, it's completely analogous to sort of the classical theory of surfaces, but if you blow up a smooth point, you're going to introduce an exceptional divisor here. And the canonical divisor will be negative on the exceptional divisor. So in other words, if you blow up a foliation, so if you sort of increase its birational complexity by blowing up a lot, you're going to introduce lots of curves where the canonical divisor is not an f. So you could think morally, the failure of the canonical divisor to be an f is detecting a lot of additional, birational complexity in the surface. And the idea of the minimal model program, which I'll describe in a bit, is to reduce that birational complexity by making kf an f. So again, the moral of this story is that failure of kf to be an f is associated with additional birational complexity, so with whatever that means. There's extra stuff floating about. And so again, if our goal is to simplify the foliation, to get to a simplest model possible, we should try to reduce this complexity, and a natural way to attempt to do that is to make kf an f. Okay. Great. Any questions so far? Okay. So in a very down-to-earth term, so the minimal model program is an algorithm which realizes the above goal. So and by above, I really mean above. So whatever the minimal, so I'll describe what the minimal model program is. But again, the whole point of the minimal model program is it's an algorithmic process to simplify the complexity, the birational complexity of a foliated surface. And what it will do is it will either turn your foliation into a P1 bundle, or it will turn it into a foliation where Kf prime is an F. So it does one of these two things. Now, how it works is much more complicated. But again, this is the big picture of what's happening. And now I'll try to get a bit into the guts of how this algorithm actually works. Okay. I'm going to bring down the third board, so that might take a while. So I guess in the meantime, I don't know, does anyone know any good jokes or anything? So yeah, okay, what I want to do now is I want to, in the case of surfaces, or give a kind of cheating explanation of how the minimal model program works. So I'll sweep some details underneath the rug. I'll try to come back to them later. So if you know the details, don't make me look bad by calling me out. Well, I guess you could. I mean, it's, I'm not too proud. Yeah. Okay. So so how are we going to do this? So how are we going to realize this goal? Well, the first thing is, so we start off. So I guess step one is to replace xf by a reduction of singularities. I.e., I want all the singular points of f to be simple, or I guess sometimes they're called reduced. I guess so. Lorena explained that this is a theorem of Seidenberg that we can always do this. For me, I guess I'm going to be using classically simple, so my eigenvalue, the ratio of my eigenvalues is not a positive rational number. So, so classically, so this is just I guess using the notation of Lorena, I'm assuming that the ratio of the eigenvalues is not a positive rational number, just to emphasize this. Okay. So let's run so step 2 is we run the following algorithm. So step 2 is if x, so we ask, is kf nef? Well, okay, this is easy. If the answer is yes, we stop. If the answer is no, we have work to do. Okay. So if it's not nef, so theorem, we use the following theorem. So again, x here is a smooth surface. F is a rank 1 foliation with reduced, or one-dimensional foliation with reduced singularities. Then if kf is not nef, then there exists a curve C inside X such that the following happens. So kf being not nef means that there exists some curve. So again, just want to emphasize, just by definition, this just means that there exists some, say, maybe I'll call this curve L and this curve C. We'll see why in a second. So there exists some C such that kf dotted with C is negative. So that's just the definition of nefness. There exists some C where it's negative. What my theorem is going to tell us, well, it's not my theorem, but what this theorem is going to tell us is that there exists actually a special curve on which kf is negative. So there exists a L such that the following happens. So L is invariant by F. So i.e., it is a leaf away from sing F, hence the L. 2, kf dotted with L is negative. It's, well, 3, L is actually isomorphic to P1. And 4, L squared is non-negative. So again, what we've done is, by definition, we have this curve C, but this curve C could be anything. It could be some garbage. It has nothing to do with the foliation. But what we can produce is, from this curve C, we can produce another curve L, which is generically a leaf of the foliation. So, non-positive, yeah, non-positive, yeah, thank you, yeah. So it should be, yeah, this one, less than or equal to 0. Thank you. So I guess for just to throw out another word, this is the cone theorem in disguise, is what I'm doing. So I want to emphasize that, so if we go back to the homework problem up there, that the exceptional divisor of the blow-up, the exceptional divisor, taking E to be L, the exceptional divisor is generically a leaf, so it's invariant by the foliation. It has negative intersection with KF, it's intersection -1. Because we blow up a smooth point, it's P1, and it has negative intersection. So I just want to remark, the exceptional divisor of the blow-up satisfies 1 through 4. So you can think about what this theorem is doing is you give it a random curve on which KF is negative, and it picks out an exceptional divisor for you. So philosophically, that's what this theorem is doing. It's hunting around your surface for something that looks like an exceptional divisor and finds it for you. Yes? So X is a smooth surface. Yeah, so my surface, yeah, so I'm thinking about with surfaces today, but we'll see that smoothness is a bit of a lie in a second. Yeah, so yeah, so maybe I'll say, yeah, so what we're doing is we're looking, we go to the Kleiman-Mori code. So I'll talk more about this next time, tomorrow. But I would say, yeah, the way the proof works is we look at the Kleiman-Mori cone. We look for an extreme array in the Kleiman-Mori cone, which is KF negative. And then we do some sort of bend and break style argument to show that there's actually a rational curve sitting inside this. Yeah, thank you.
So it's the same as algebraic.
Exactly, yeah, it's precisely. Okay, great. Any other questions on this theorem? So I won't prove this theorem, but I'll try to say more about it later. Okay. So what's the next step? So we've found our curve. Our next step is to contract it. So this one is. So theorem. So the next theorem is, so let L be as before. So L is our L coming from the theorem 1, or cone theorem. Then there exists a map, or a map P x to y, such that P of L is a point. So we can contract L to a point. But there's a bit more, because, well, I guess, y could be a point, and this would be true. So we have to impose a few more hypotheses here. So the first one is that if L squared is 0, so remember we have two possibilities, either L squared is 0 or it's strictly negative. If L squared is 0, then P is a P1 bundle. One bundle. And F comes from this bundle structure. So we get into one of our two target cases, namely a bundle structure. So in this case, actually, the minimal model program would terminate. So when L squared is equal to 0, we found the bundle structure we were searching after, and we're done. Oh yeah, perfect. Yeah, it's even better. Yeah, thank you. So this is going to work out very nicely. So yeah, beautiful. Thank you. Yeah, it was all planned. Yeah, this was, it was supposed to be this way. Yeah, thanks. I owe you one. So in case 2, so if L squared is negative, then P is birational. And contracts only L. So I would love to say that, oh, okay, perfect, we're in this case now. That's not quite true. We've contracted one curve, but maybe there are lots of other curves on which KF is negative. But the idea is that in this case, maybe ultimately we hope that we're sort of ending up in this case, but it's not exactly true. What we have to do actually in this case is, no, I want to leave this up. Let's go take this one down. So again, in this case, L squared is negative, so the contraction is birational and it contracts only L. So again, in the case where L is the exceptional curve of a blow-up, this morphism P is just doing the exact opposite of a blow-up. It's a blow down. So now what we'd like to do, so we want to replace x by y and continue the process. So we've contracted our curve. So we have this curve, so here's L. We're contracting L down to a point. So here's P of L here. And then we want to basically just rerun the whole process again. So if it's Neff, we stop. If it's not Neff, we hunt around for another curve using the cone theorem. So using the cone theorem. So if it's not Neff, we'd hunt around for another curve using the cone theorem, and then find it, and then contract it, and then just continue. This process can only happen finitely many times, because at each step, well, topologically a sphere, L is just a P1, it's a sphere, and so at every step, the second Betti number is dropping. And so the second Betti number being a finite number can only drop positive. I guess that's a useful point. Yeah, the second Betti being a finite positive integer can only decrease finitely many times. And so this process will terminate. There's a small rub. So the issue is that in contrast to, so if you know something about the minimal model theory for surfaces, so in contrast to the minimal model theory of surfaces, y is usually singular as a variety. So usually, problem, y is singular. Now, up until this point, I've assumed that all my surfaces were smooth. This tells us that if we want to actually realize this dream of this minimal model program, we have to work with singular varieties. And this is just a fact of life about the minimal model program. So you should think that in the minimal model program, there's a tension. There's a tension between simplifying the global geometry of a variety at the cost of making the local geometry a bit worse. So you try to simplify the global geometry by contracting things, but in the process of doing so, you introduce singularities on your underlying variety. So to handle this, we have to develop a new perspective on singularities. So I want to now, for the last little bit, is talk a bit about what this perspective on singularities is. So I'll say that, so maybe just to write a quick summary. So up to this issue with singularities of y, this process realizes our initial goal. So again, up to, I somehow have to convince you that we can contend with these singularities, but up to the fact that y might be singular, we have really completed the goal up on the top right-hand pane there. Okay, so I guess this you know, deserves a breather maybe and a pause, just to see if there's any questions. So again, I'm going to shift away from talking about globally what the MMP is doing, so globally about what this process is doing, and we're going to spend some time now talking about the singularities and what the perspective on singularities we're going to use to handle these problems. Cool. Any questions? Yes, that's a very good point. So, well, hopefully I'll be able to say something about this. Yeah, a priori, if you have very bad, so I guess what we'll see is that if you have very bad singularities, you usually expect a reduction of singularities to change the numerical properties of the canonical bundle wildly. So you could have bad singularities and KF could be ample. You go to a resolution and KF could be not pseudo-effective anymore. This is possible, so it can completely change. Again, I guess the benefit of this perspective, the MMP perspective on singularities, is that this perspective will explain exactly why this might happen. So a lot can happen, a lot in terms of global geometry can happen with a resolution of singularities. So you have to be very sensitive about that fact, yes. Thank you. Any other questions? So MMP. Yeah.
When you make the reduction process, is it possible to find first a curve with S squared strictly negative, then contract it, and then find a curve with S squared equals 0, and so you have a P1 bundle?
Yes, yeah, exactly. That could happen. Yes, precisely. So yeah, I guess yeah. So the prototype example. So yeah, just to emphasize that yeah, this could happen is actually yeah. Let's do maybe let's do a concrete example together because this will be useful. So let's say I start off with a P1 bundle over a curve C. So here's a P1 just given to me, and then I blow up a point on it. Maybe I started to, let me start a bit lower. Here's C. Oh yeah, you're right. Okay, thank you. And I need to be a bit taller here for this, but okay. So here's our P1, but yeah, this is, I'll bring it back down to draw and then I'll bring it back up. Okay, so here's our P1 bundle, and let's blow up a point on the P1 bundle. So I'll bring this down, draw my picture, and then. So when I blow up the P1 bundle, I'm gonna break a fiber, I'm gonna get a broken fiber. I'm gonna get a fiber which consists, that looks like this. Now, on each of these components, we know that Ci squared is negative. So starting from this thing, my algorithm will tell me we'll hunt around for a curve. It'll pick one of the CIs. It'll pick one of the CIs and then contract it.
The way you explained, not necessarily.
So I guess that's what I'm lying about a bit about. We always want to choose it to be extremal. So I guess so for people in the know, we're always choosing our CI to be extremal. I'll come back around to what I mean by extremal in a bit, but I didn't want to throw the Kleiman-Mori cone in front of you at the first blush because I thought that might be a bit excessive. But I promise you, I'll make everything correct in the end. I promise. My theorem with cheating and George's help, we'll choose CI. We'll choose one of these CIs, and then it will contract it. So we have our first step of the MMP is a birational contraction, which is undoing a blow up. And then the second step of the MMP will be the P1 bundle we're going for. There's, I guess there's a slight subtlety to be aware of, is that we could have, the MMP is non-deterministic. It depends on choices you make. So let's say that C1 is the exceptional blow-up divisor here. We could have contracted C2 also. So actually, the program could have run two different ways. They both end up in P1 bundles, but it could have run two different ways. So this sends C1 to a point, and this one sends C2 to a point. In either case, we end up with a P1 bundle structure. So our first step is a birational contraction followed by a bundle structure, but there are two different bundles we could get. But we always end up with a bundle. So there's a slight subtlety there. Yes, thank you for your question. So yeah, we could start off with birational contractions and end in a P1 bundle. Okay, great. Any other questions about global geometry before I start talking about singularities? So the idea with the MMP and singularities is we're going to measure singularities using the canonical bundle, or canonical divisor. So, so again, XF is a foliated surface. And let's say, and let P from X tilde to X be a sequence of blowups. And let tilde F be the transformed foliation. So well, we know that these two foliations are completely isomorphic outside of the exceptional locus. So what it tells us is that, well, KF tilde and KF away from the exceptional locus have to be the same thing because it's canonical divisor associated to something, but it's the same thing, so they have to be the same away from the exceptional locus. In other words, they can only differ by on some divisors which are P exceptional. So where the EIs are P exceptional, and the AFEIs are just some numbers. So it's a rational number called the discrepancy. Because it measures the discrepancy between the canonical divisor upstairs and the canonical divisor downstairs. So we cook up a bunch of these numbers. And the idea with the MMP perspective on singularities is that it's these numbers which we should look at to understand singularities. These are the key. So we associate these numbers. I mean, to every valuation, we have this number we associate to it. And the MMP perspective is to study singularities using these numbers. And so I'm going to define some singularities for you. So not as, yeah, so, okay, yeah. So yeah, you may want to remark, so if X is smooth, and so KF is a line bundle, then these are all integers. You're absolutely right. But so I'll give an example. Yeah, so in general, yeah, we just have. So actually, this example is another good exercise for PhD students. Take consider the following quotient of C2. So take a quotient of C2 by the action of so xy goes to negative x, negative y. So this will be this quotient will be a singular surface. So in fact, it's going to be uv minus w squared inside C3. And take the foliation on C2. Well, we have a foliation defined by partial x. This is invariant underneath the action of this. I mean, the foliation generated by partial x is invariant by this group action. But this generator is not. So this descends to a foliation on this singular point, v squared, such that TF is not a line bundle. But TF, the second tensor power of it, is. So it's a Q-line bundle. So this is something to be aware of. And in this case, if you resolve this singularity, you'll see that the discrepancies actually can really be rational numbers. So this really does happen. But of course, yeah, as you say, when F is a line bundle, they're just integers. In fact, it would be the rational number 1/2. So yeah, so let's so yeah, this is continue the exercise. So this can be blown up, resolved by a single blow up at the singular point. It extracts a rational curve E, such that E squared is minus 2, and the discrepancy of this blow up with respect to F is exactly 1/2. So this is a very nice exercise to try to work this all out. Sorry, I didn't hear you. Yeah. Yeah. So this one, yeah, so I will say that in my opinion, this is a perfectly good point. It's what I will call a terminal singularity. Well, okay, yeah, so maybe from the perspective of the minimal model program, this is totally acceptable. And I guess intuitively, it's just a quotient of a smooth foliation, which is pretty nice. So like it's an orbifold smooth point. So philosophically, we should just leave these points alone. The MMP will do that for us. The MMP says, nah, that's fine, let's go on. But yeah, we'll circle back around to that. But yes, thank you. Okay, so I have 5 minutes left. So I would like then to define the class of two of our relevant classes of singularities, and then quickly relate those to the classes of singularities that Lorena mentioned earlier, just to bring things full circle. So in this definition, we say that F has canonical singularities if A, E, I, F, so these numbers are always bigger than or equal to 0. For any p, exactly, yeah. So I'm imagining p runs over any possible birational model. So if you want, you could think that this is just some divisorial valuation, and I'm just computing the discrepancies with respect to any possible divisorial valuation. So yeah, for all possible EI and P. Yeah, so I want to emphasize, yeah, George is right. Yeah, this is really for all possible modifications. It has log canonical singularities if A, E, I, F is bigger than, now we have to do a little work, so bigger than 0 if EI is invariant, and -1 if EI is not invariant. And there are two other classes, terminal and log terminal, but maybe I'll say more about those tomorrow. I don't want to just overburden you by throwing out a bunch of definitions all at once without saying more about it. But these are our two important classes of singularities we want to work with from the perspective of the MMP. Yes, exactly, yeah. So really we should be working with TF log the exceptional divisor. This is really the correct setup. Yeah, that's absolutely correct, yeah. Any other observations or comments? Oh, thank you. Okay, so yeah, I should say there's a more refined and I guess more functorial perspective on this whole story. But I guess in the interest of keeping this as down to earth as possible, I want to emphasize this aspect of it. So, so from Lorena's talk, there were two important classes of singularities: elementary singularities and reduced singularities. So, okay, so we have, so recall elementary singularities just means that it's either a smooth point or the linear point part of the vector field defining the foliation has a non-nilpotent linear part. And then inside elementary singularities are reduced singularities, or simple. Okay, so over here we have log canonical. And sitting inside, and I guess evidently, everything which is canonical is also log canonical. So every log canonical singularity is definitely canonical. Okay, if X is smooth, these are the same thing. So, but I want to emphasize one of the strengths of the MMP is in this definition, I don't assume X is smooth anywhere. I can really work with singular varieties. And again, we have to work with singular varieties. This is crucial. So I want to emphasize that from the MMP's perspective, these singularities really make sense on any variety. Any normal variety, thank you. Yes, so X is smooth surface, yeah. For vector fields, I guess if you define an elementary vector field to be one with a non-nilpotent linear part, then this continues to be true in any dimension. So yeah, I guess with the proper setup, I guess the natural generalization of this, it's true in all dimensions, but for vector fields. Elementary vector fields are always log canonical, and vice versa on a smooth thing. So, so these two, so again, to get a handle on what's going on in these classes of singularities, you should just, I mean, if you know elementary singularities, you already know log canonical. Reduced singularities are always canonical. And I guess depending on your definition of reduced, it's a strict inclusion. The example is, look at the vector field x partial x plus y partial y. I guess in Seidenberg's definition, so this is not a reduced singularity, but it is canonical. So this is not reduced. Is canonical. So for the rest of my talk, or the rest of these talks, if you just want to help you, think about what's going on when I say canonical and log canonical, you can replace those by reduced and elementary, and you won't lose too much of the picture. But again, you know, the benefit is that we can work with singular varieties. Okay, I guess I'm out of time, so I'll stop here, and thank you very much.
So thanks a lot, Calum. So are there questions, remarks?
Is there a class of singularities in the MMP terms that corresponds to the reduced simple ones?
So as far as I know, there's no clear way to distinguish, just using these numbers, there's no way to distinguish these two classes, as far as I know. I mean, I guess when you blow this up, you get, I guess, yeah, fundamentally the issue is this, is that there's no MMP way to distinguish saddle nodes from non-saddle nodes, as far as I can tell. And that's somehow the heart of it. So you need some way to distinguish saddle nodes and non-saddle nodes using, you know, these discrepancies, which, to my knowledge, is not possible. Yeah. Sorry.
Any other question, remark? In that case, let's thank the speaker again.